Hi everyone, what I want to do is go over the last two problems, number 5 and the bonus. So for 5, let M be a subspace of X. Show that there is an isometric map from M star to X star. Okay. And let's use the hint. Right. Okay, so the hint was, I'll just rewrite the hint. Let's say we have something in M star star. So it's a bounded linear functional on M star. And sorry, let's say psi here is an M star star. So define psi tilde that's a bounded linear functional on X star. So let's be a little careful and unravel this. I want to take something in X star and plug this in. So this phi here, var phi rather, is a bounded linear functional on X star. It's a bounded linear functional on X, not X star. It's a bounded linear functional on X. I can restrict that to M to get a bounded linear functional on M. No reason why I can't do that. So we're going to define this to be psi here, where I plug in this bounded linear functional on M. Right. And well, so this here is itself a bounded linear functional on M star, so this makes perfect sense. And as you can check, this is a bounded linear functional on M. I mean, certainly bounded, because this is bounded. Var phi is bounded. And it's certainly going to be linear, because this is linear. Okay, so this is going to be my map. And let's check this is isometric. So let's just write down all these definitions here. Okay, so yeah, so the dual space norm is just the usual one, the supremum over all bounded linear functionals on M star, or sorry, all bounded linear functionals on M. Move this away. Yeah, and again, just to remind you, this is a bounded linear functional on M star, and the norm is 1. Whereas this here, again, just write down the definition. Same thing, except we're looking at bounded linear functionals on X with norm 1. Right. So this is just going to be, by definition, psi with phi restricted to M. Right? And again, just this here is going to be, this is a bounded linear functional on M. So this makes perfect sense. Okay, so let's say this is 1. Let's say this is 2. So we want to prove that 1 equals 2 for each psi in M star star. And it's a bit tricky to unravel everything, but it's really just a Hahn-Banach theorem. One direction is actually not even that. Right? And that's what we need to do to prove that our map is isometry. Okay, so right, so this is the norm of psi tilde. So subtract epsilon. That's no longer an upper bound because the sup is the least upper bound. Okay, so we can pick bounded linear functional on X with norm 1, where, well, subtract epsilon from the operator norm. This is going to be less than, oh, really less than, right? Less than or equal to just this here. Well, this is going to be less than or equal to, well, this is still a bounded linear functional on M star, so it's just the norm times the norm make this a little neater. Sorry about that. Give myself a little bit more room. What's this? Okay, yeah, and this is, again, less than or equal to just the norm of psi, this one here, times the norm of phi restricted to M. Yeah, as a bounded linear functional on M. Well, just write down a definition here. It's just the sup over all little m norm 1 of, well, phi restricted to M is phi. So obviously this is less than or equal to the whole operator norm of phi, or operator norm, the norm as a bounded linear functional on X, because they were looking at all X with norm 1 in big X. Well, this is norm 1. That's how we chose it. Right, so that means 1 is less than or equal to 2. This is 1, this is 2. So now let's prove 2 is less than or equal to 1. Basically do the same thing, right? So for this epsilon bigger than 0, pick, we want to, sorry, we just proved that 2 is less than or equal to 1, not 1 is less than or equal to 2. Right, so now pick something where the norm as a bounded linear functional on M is 1. Again, just definition of a soup. Subtract epsilon, it's no longer an upper bound, so this is less than, really less than or equal to, in particular, psi with phi plugged in. Okay, well, let's say phi tilde is a Hahn-Banach extension. So remember, this is, well, this is an, obviously, M star star. So we're only looking at bounded linear functionals really on M when I plug in to psi. So yeah, let's say this is a, sorry. So phi var phi tilde, I'll do this in green. Of phi to M, right? Okay, so this is less than or equal to well, really, what's this equal to? This, by definition, is psi tilde. Sorry about that. This, by definition, is psi tilde of var phi tilde. Right? Remember what the definition was. It's just we plug in something in X star, and then we restrict it to M, and apply psi. Right? This is certainly as a Hahn-Banach extension in X star. Right? Right, so this is going to be just less than or equal to, well, the norm of psi tilde times the norm of phi tilde. Well, as a Hahn-Banach extension, this equals a norm of phi, which is 1. So this is X star star. Right, and that proves it. So yeah, it's a huge pain in the ass to unravel everything, but it's really just a Hahn-Banach theorem. Okay, so yeah, what does this prove? This proves that 1 is less than or equal to 2. This is 1 here, minus epsilon. This is 2. This is true for any epsilon, so 1 is less than or equal to 2. So 1 equals 2. So one thing some people did was they said, well, M is a subspace, it's fine, of X. So M star is a subspace of X star. Well, this isn't really true. The best you can do is define an isometric map from M star to X star. Right? So what you can do, I notice I didn't say linear. Right, so you can just define this isometric map using Hahn-Banach theorem. So given phi and M star, let phi tilde be a Hahn-Banach extension. To X. So it's norm preserving. So yeah, in this regard, you can kind of embed M star into X star. I don't know, let's say let's say L, I don't know what the so L of phi is just phi tilde. On the other hand, the issue is what is L of, let's say, phi 1 and phi 2 are bounded linear functionals on M star. What is this? I have no idea. I have no idea because the Hahn-Banach theorem just says there exists a norm-preserving extension to all of X, given a bounded linear functional on M. We have no idea what it is. We used Zorn's lemma, which basically is basically the axiom of choice. I always forget if it's equivalent to the axiom of choice. Never bothered to go too deeply into set theory, but the point is it's not constructive at all. We don't know. We have no idea what this is. We just know it exists. So this is an M star, M star. We have absolutely no idea what it is. So we do not know that L of M star is a linear subspace. So you really can't say M star is a subspace of X star. You can define M star as a subset of X star in the sense of this L, but it's really not a linear subspace. So it's certainly isometric, that's fine. Okay, so I want to do the bonus problem, which is if M is a closed subspace of a reflexive space, then M is also reflexive. And I'm going to use the basic construction of 5 to do this, right? So, okay, so the bonus. All right, so, right, let's say I have something in M star star. Okay. Just like before, define psi tilde phi for this and X star star by phi tilde of phi equals psi tilde phi psi of phi restricted to M. And I forgot to say, this will be an element of the double dual X star star. You can check that very easily. Right. Okay, well, X is reflexive. So I can pick an X0 in X, where, by just nothing more than definition of reflexivity, psi tilde is given by X0 star star, meaning that, psi tilde is given by just evaluation at X0. So remember, sorry, so this actually is an X star, right? Phi is an X star. So we can plug in X0, that makes sense, okay? Okay, so first of all, I want to prove, and after I do this, we're basically going to be done, as we'll see in a second. I claim that X0 is an M, the closure of M. Well, we're assuming that M is a closed subspace, so the closure is M itself. Okay, so how do I do this? Well, let's go back to that wonderful will result on page 51. Okay. The last sentence of corollary 3.6. So X0 is in the closure of M if and only if there's no bounded linear functional on X when restricted to M is 0 and is not 0 at X0. So let's take a bounded linear functional when restricted to M is 0. And let's see what happens. Okay? We need to show that for any such bounded linear functional, we're going to get 0 when we plug in X0. Right. Okay, so let's say we're given something in X star when restricted to M is 0. Right, so let's just plug in. So remember, this is going to be psi. So it's very deceptively simple, this part. So by definition, this is psi of phi of M. This is for any bounded linear functional on X whatsoever. And this is going to be equal to, well, this is 0. We're assuming this is the 0 functional on M. Phi restricted to M is 0. And this is in M star star. So this is just a 0 linear functional on M. So plug in 0, you get 0. So this is going to be 0. So by corollary 3.6, plug x0 into any bounded linear functional that vanishes on M. We get 0. That implies x0 is an M closure, is an M. Okay. Now let's finish up the proof. Okay, so now instead, let's say we're given something in M star. Okay. So let's say this is a, you don't even really need a Hahn-Banach extension. Any extension works. You don't need norm preserving, but let's say it's a Hahn-Banach extension. Of var phi to x. Right? Okay, so plug x0 in. This is going to be, well, x0 is an M. So we're going to get its Hahn-Banach extension. This is defined on M. This is a Hahn-Banach extension. This is an M, so phi is phi tilde on M. Okay, this is by definition, or the way we picked x0 using reflexivity, it's psi. Remember, we started off with psi, and we want to show that it's given by something in M. Okay. This is psi of phi, var phi, I keep saying phi, it's really var phi, restricted to M. Well, here it's phi tilde. Well, this is a Hahn-Banach extension, so it's an extension. So this is psi of phi. So we've proven that given any psi in M star star, there exists x0 in M where this is given by 5x0 for anything in M star, or in other words, this is given by x0 star star. That's exactly the definition of reflexivity.